Module 4, Ohm's Law and Series Parallel Circuits. This is a typical circuit that includes both a series section and a parallel section in the circuit. In previous modules, in Module 1, you learned about Ohm's Law rules and theory. In Module 2, you learned about series circuits. And in Module 3, you learned about parallel circuits, but here it's a combination of both series and parallel in the same circuit. A series parallel circuit has a portion of the circuit in series with a parallel section. If one component of the parallel section burns out, all the other components remain on. However, if the series portion before the parallel section burns out, the entire circuit is disabled. This is a typical series parallel circuit. Here we have three resistors, a 10 ohm, 15 ohm, and 30 ohm resistors, R2, R3, R4. They are all in parallel. And they're in series with one resistor, R1, which is 55 ohms. Our total voltage is 120 volts. The series parallel circuit must be analyzed separately. In general, it is best to start at the end farthest from the voltage source. The goal is to continuously simplify the circuit until there is only one equivalent total resistor. You will need to apply the rules for both series and parallel circuits, each separately in separate matrices. Resistors that are in parallel or series behave as if they are a single equivalent resistor. For example, two 100 ohm resistors in series act as one equivalent 200 ohm resistor. Two 100 ohm resistors in parallel act as one equivalent 50 ohm resistor. Let's look at the series parallel circuit again from slide number 3. Here we have three resistors in parallel, a 10 ohm, a 15 ohm, and a 30 ohm, and we have in series with this parallel section is 55 ohm resistor at R1. These three act as if they're one resistor, and this in series with these three, once we find the equivalent resistor, will act as one resistor. Again, here's a review of the series parallel rules. Voltage in a series circuit is the sum of all the voltage drops. E1 plus E2 plus E3 equals ET. Parallel circuit, the voltage is the same everywhere. ET, total voltage, equals the voltage at E1, also equals the voltage at E2, also equals the voltage at A3. It is the same. It's the opposite in the series circuit. Series circuit, current is the same everywhere. IT is the same as at I1, as at I2, as at I3, and then our total current in a parallel circuit is the summation of all the currents. I1 plus I2 plus I3 equals IT. Resistance. Total resistance, RT equals R1 plus R2 plus R3 in a series circuit, but in a parallel circuit, RT equals 1 over R1 plus 1 over R2 plus 1 over R3. We call this the reciprocal of the sum of the reciprocals. Power is the sum of all the powers to give us the total power. Both series and parallel are the same. Here we're going to set up one matrix. We're going to call it matrix 1 dash P. P tells us it is a parallel section, so we're going to use parallel rules. We have R2 is 10 ohms, R3 is 15 ohms, R4 is 30 ohms. Using this scary formula, and we're going to show you how to do it very quickly. It is not that hard to do once you understand it. Is that we have 1 over 10 plus 1 over 15 plus 1 over 30. It gives us 5 ohms. We're going to call that RA. It's an equivalent resistor. It's just a holding place so that we can use this value somewhere else. Total resistance, again, in a parallel circuit is the reciprocal of the sum of the reciprocals. And here we have it, 10, 15, 30 in parallel, 5 ohms. Again, this 5 ohms must be less than the lowest resistor in value. If you get a number larger than that, go back to your calculator and recalculate. Here's the formula. 1 over 1 over 10 plus 1 over 15 plus 1 over 30, and it's also the reciprocal. We have, looking at it now, we're just going to worry about the reciprocals on the bottom, not up here right now. We have 1/10 plus 1/15 plus 1/30. We're going to take a common denominator. I can see 10 will divide into 30 and 15 will divide into 30. So we're going to use this common denominator of 30. Then we're going to divide. 10 goes into 30 3 times. 1 times 3. 15 divides into 30 2 times. 1 times 2. 30 divides into 30 1 times. 1 times 1. Now looking at it, 1 times 3 is 3. We have a plus sign, so I put a plus. 1 times 2 is 2. We have a plus sign, so we put a plus. 1 times 1 is 1. We have 3 plus 2 plus 1 equals 6 over 30. And this is 1 over 6 over 30. Whenever we divide a fraction into another number, whole or fractional number, it's the same as multiplying by its reciprocal. So it would be 1 times 30 over 6. And since 1 is not going to change the value, I don't have to worry about this. All I have to do to remember is that when I get this value, I'm just going to take its reciprocal. I'm going to flip it. It becomes 30 divided by 6 equals 5 ohms. That's how easy it is to do parallel resistors using this formula. So now I'm going to take that 5 ohms, right, here, and we're going to be putting it into the next matrix, series parallel. We can't just put the total voltage up here at RA because it is not going back. Let's look at this voltage that we had, 120 volts. I can't put that there because guess what? Get right here. This is going to change. I have 120 volts dropping. I can't figure that I'm going to drop so much voltage on 55 volt 55 ohm resistor because I must know this value before I can find out the proportional drop for each of them. So in a series parallel, we can't just put the voltage for the resistors R2, R3, and R4 because we are first dropping voltage across the 55 ohm R1 resistor. We must take the information we have for RA and make a new series matrix. Use the ohms and power formula wheel on the next slide to calculate the unknown values of current and power. Here's those two formula wheels. This is the Ohms Law wheel. This is the power wheel. This is voltage, current, resistance, power, current, voltage. Stop your video here if you have to. Make a drawing of this because it will help you using the formulas. This is this new matrix. This is matrix 2-S. This is a series circuit now. Here's RA. All we know about it right now is that 5 ohms, which we calculated in matrix 1, the parallel one. And we know that we have 55 ohms at R1 in the series section, and we have 120 volts. Resistance in a series circuit is the summation. 55 plus 5 equals 60. So 60, now I want to find my amperage. I have 120 volts. I have 60 ohms. I have I equals E divided by R. E divided by R, 120 divided by 60 equals 2 amps. This is a series circuit, so the current is the same everywhere. Now I have I times R, which is I times R, 2 times 55 equals 110 volts. And 2 times 10 equals, 2 times 5 equals 10 volts. 10 volts plus 110 equals 120 volts. Now I know I'm dropping 110 volts at R1, and across the parallel resistors I'm dropping 10 volts. Power is E times I, or I times E. 2 times 120 is 240. 2 times 110 is 220. 2 times 10 is 20. 20 plus 220 is 240. We can now take all the information from RA in the previous slide. Let's go back to this. We figured out everything for RA now. 10 volts, 2 amps, 5 ohms, 20 watts. We go back to matrix 1. This is parallel matrix again. And we put in all these values for RA because now we can use it to calculate everything else. We know R4 is 30 ohms. We know R3 is 15 ohms. We know R2 is 10 ohms. And we know RA, the equivalent resistor, is 5 ohms. Okay? So now we want to be able to, you notice here we have 10 volts. So I can go, and I have 2 amps. 10 volts, guess what? This is a parallel circuit, so the voltage is the same everywhere. 10 volts, 10 volts, 10 volts. So now I can find my current for these other values. 10 volts divided by 10, E divided by R equals 1 amp. 10 divided by 15 equals 2/3 of an amp. And 10 volts divided by 30 ohms gives me 1/3 of an amp. Likewise with my power, 1 times 10 is 10 watts. 2/3 times 10 volts is 6 2/3 watts. And 1/3 times 10 is 3 1/3 watts. I have all the values that I need now. Looking at all this information, dropping out RA, we can look at all the values, my total values for the whole circuit: 120 volts, 2 amps, 60 ohms, 240 watts. At R1, I'm dropping 110 volts, I have 2 amps, and I have 55 ohms, and I have 220 watts. At R2, 10 volts, R2, R3, R4, it's all 10 volts. I have 1 amp at R2, 2/3 of an amp at R3, 1/3 of an amp at R4. The resistance hasn't changed. 10 watts, 6 2/3 watts, and 3 1/3 watts. If we built this circuit and we put the proper voltage to it and these ohms were exact, we would be able to take a meter and read every one of these values and they would concur. The theory actually works. Here's basically similar circuit, except we have 2 resistors in series with 3 resistors in parallel. They're all 1200 ohms, and we have a 28 volt supply. 1200 ohms plus 1200 ohms plus 1200 ohms equals 400 ohms. When you have similar resistors with all the same value and you have 3 of them, you just take the value and divide by 3. If I had 4 resistors, it would be the same value divided by 4. Here, 1200 divided by 3 equals 400 ohms. This is matrix 1. It is parallel. RA, all I know right now is 400 ohms. I can't do anything else because I don't know the voltage drop or the current yet. I take that RA and I put the information into a new matrix, matrix 2-S. This is a series circuit, second matrix. Here's RA, but all I know is the 400 ohms. I know in the series portion, I have 2 1200 ohms resistors in series. So 400 plus 1200 plus 1200 equals 2800. I have 28 volts. 28 divided by 2800 rather, 0.01 amps. This is a series circuit, so the amps are the same everywhere. Now I can find my voltage drop. Amperage I times R equals E, so 0.01 times 1200 equals 12 volts. The same here, 0.01 times 1200 equals 12 volts. 0.01 times 400 ohms equals 4 volts. My power is I times Z on all of them, and it will give us 0.28 watts, 0.12 watts, 0.12 watts, 0.04 watts. Now I can take all this information of RA, which is calculated, and put it in my first matrix, matrix 1-P. Here it is, all the information. We have all the resistor values, 1200, 1200, 1200, 400 ohms. And we have RA is 4 volts, right? So everything is the same on voltage because it's a parallel circuit. I have 4 volts drop on each one of these. 0.01 times, I times the 0.01 times 4 gives me 0.04 watts. 0.003 times 4 gives me 0.013. These are rounded off. 0.003 times 4 gives me 0.013 watts. My amperage is the same here everywhere. This is my total thing. So now putting this all together, we find out everything. If I built this circuit, I can test for these values and find that they actually work. This concludes the instructional portion of this module. In Module 5, you will learn a simple system of circuit analysis. Basically, we've been doing it, but we'll define it a little bit more in the next module. Be sure to click on the link below to take the online quiz, and as always, if you need to, go back and review all the modules in this series, Module 1, Module 2, Module 3, and this module until you understand the information provided.